general relativity step by step. I was going to try and find m00, and the first observation I want to make is that m00 equals some function of v, which is the relative motion of the two coordinate frames. So what I'm going to do is I'm going to consider a rod. There it is, a rod, and I'm going to move it at right angles to itself. So v is in a particular direction, and I'm going to consider this rod at right angles to itself, at right angles to the relative velocity. It's pretty clear that the rod itself can't change its length. The kind of argument that you see for that is that if you can construct a railway here, this is supposed to be a railway, and you move a train along that railway at a very high speed v, 9 times the speed of light. If you look at what you see the train track as it goes away from you, it's got these here are the tracks. I'll draw that in a slightly different colour. Let's draw that in green. These are the tracks here, which are written in green, and here are the wheels of the train. Now, there's absolutely no way, even if that train is moving along at 99% the speed of light, those wheels sit on that track. And there's no way different observers can argue about this. I mean, if one observer sees the wheels inside the track, then they're inside the track, and everyone will agree on that. I can't imagine a world in which I say they're on the inside of the track and somebody else says they're on the outside of the track. I mean, if I draw my wheels like that, that's a very different situation from the track looking like this and the wheels being on the outside of the track. They'd need to cross over the wheels would need to cross over the track and go from the inside to the outside, and that simply can't happen. So if we have a look at this rod here, if I go back to black for a second, we can set up the coordinates like this. That there can be the x-axis, this is the t-axis, this might be the y-axis, and here's my rod along there. So its world lines look like that. And there is my velocity v. So, because the rod can't change its length, when you move at this velocity at right angles to the rod itself. And space is isotropic. So it can't depend upon the direction either. The only thing that can possibly change is the time, as measured by the observer moving with the rod or the observer moving at rest with respect to this coordinate system here. So what that tells me is that my function equals f of v equals f of the modulus of v, because it cannot depend directly due to the isotropic nature of space. It cannot depend on the direction of the relative velocity, but it can depend upon the absolute velocity itself through variation of the time element of the matrix there. Okay, so that's the first part of the proof, and now what I want to show is that f of v. So I guess I could call it f of v, where v equals modulus of v underline equals plus or minus 1. How do I show that? Well, I'll do that in the next screencast, because I want to keep these screencasts short and sweet. I don't want them to go on. I think some of the earlier ones went on far too long. One of them was 20 minutes. I think that's too long for anybody. I'll establish this result in the next screencast, so I'm going to stop there. Stop.